Please start, ma'am.
Thank you. A very good morning to one and all present here. I'm Mrs. D. Mukherjee, and I welcome you all to the third edition of the Back to School series, episode 6. We at Mahadeva Birla World Academy are constantly striving to modify pedagogical strategies and nurture the 21st century skills for developing and enhancing students' competencies. The back to school sessions are a way to open the world of opportunities, ideas, and options for our students. It is a job shadowing initiative taken up by our school for the holistic development of students through experiential learning. Students learn to reflect and conceptualize independently through an active interaction with their environment. Job shadowing encourages creative and critical thinking and prepares one to anticipate and face challenges. It boosts continuous development and improvement of various abilities that our students need to contribute positively to the society and be responsible citizens of the world. This is also an opportunity for them to build their network and learn from each other to get ready for life beyond school. Since last year, our school has been conducting virtual sessions with professionals and experts from different fields, and even with our qualified and very successful alumni who shared their valuable insights and experiences, thus inspiring and guiding our students to pursue their dream career. Today, we are privileged to have with us Dr. SUBARNA Bhattacharya, an alumna of MBWA, who's going to enrich us with her knowledge on the very relevant and important topic of climate change. We are extremely happy and proud to have you as our guest speaker, ma'am. I would also like to extend a warm welcome to Mrs. S. Chaudhary and her students from Birla Divya Jyoti School, Siliguri, and other guests who have joined us for this session. May I request Somdatta Chakraborty to introduce our esteemed guest of the day. Over to you, Somdatta.
Thank you, ma'am. Good morning, everyone. For today's session of job shadowing, we have amongst us Dr. SUBARNA Bhattacharya, an alumna of Mahadevi Birla World Academy from the batch of 1990. Dr. Bhattacharya is the co-founder and CEO of Climeformatics, the winner of the Cleantech Open 2014 Western US Finalist Award, set up with the novel idea to predict climate towards an environmentally sustainable future. Her passion for climate data science led her to research at Lawrence Livermore National Laboratory with the International Panel for Climate Change, a Nobel Prize winning group simulating abrupt climate change using global climate models. With a double master's degree in engineering as well as a PhD in engineering mechanics, Dr. Bhattacharya applies interdisciplinary, analytical, and data science tools to understand and predict climate data. Her recent work includes developing solutions for an improved wildlife risk assessment and mitigation. She has been invited as a guest speaker at Caltech, Columbia University, UC Davis, IBM, and the Climate Risk and Insurance Summit, and has published several articles in leading academic journals. Besides work, Dr. Bhattacharya takes keen interest in Indian classical music, and she often participates in Indian music concerts. She lives in the San Francisco Bay Area in California with her husband and 2 sons. Ma'am, we are honored to have you with us today. I would request you to kindly share a few words about yourself and take us through your journey, enlightening us with your experiences and insights. Over to you, ma'am.
Thank you so much. Shumdatta, and I am so overwhelmed to be here. Um, I'm almost overwhelmed with emotion. It's wonderful to connect to young minds, particularly, and share the journey that I have been through, and the foundations of which actually started from what we used to call the Mahadev Birla Girls High School. Today, it is wonderful to reflect back in some ways the wonderful all-rounded education we have received from our school, from our teachers, and the foundations of values, problems to pursue, all of that exposure were getting, gradually fitting in like puzzle pieces as we were growing up through our several activities, curricula, the various subjects we were exposed to at an early age, and the rigor to do it all, to pursue and not leave it. So, before I go into my journey into climate change and the hows and whys of how we got there, how I got there, let me share some of my thanks and gratitude to my most favorite, teachers in school. They laid our foundation, my foundation, um, in not only education but a lot of moral values, science values, ethics, humanitarian values that we learned from them. Um, Particularly my class teacher, at the middle to high school, our class teachers, Miss Muhare, physics teacher, our Miss Tire, we used to call her Miss Tire. Um, so they were like phenomenal in shaping our ideas. Later in the high school, we had so many good teachers, Mrs. Ipol, Miss Gopasina. We had our geography teachers, math teachers, music teachers, English teachers. I mean, I cannot remember. I took up elective English and it was so hard, but had it not been for the teachers, Mrs. Kakkar, we wouldn't have made it. So there are so many names that come to my mind that I can spend the whole hour talking about my reflection stuff that I learned from school. But one thing I would like to mention that at the very early age, when we started the middle school, we were introduced to this regular assembly of, prayers. The day used to start with prayers and we used to assemble in the hall. And every day we will kind of, learn from the teachers that we have to do some things every day without fail, like drills. And the day used to start with prayers, and we used to be a small group of people who will sing hymns, prayer songs, and that made a huge difference. We don't know, we don't understand it at that time, but as we reflect now, that with those regular routines of starting our days with prayers, that goes a long way. So anyway, let me take you a little bit through the climate change story that I wanted to share. Let's start at the very beginning, where my interest in the climate, or atmospheric science, earth science, stems from the very early age. We used to get newspapers at home, and the only thing that used to catch my interest at that time was what was written as, how will today's day turn up? It's going to be hot, it's going to be rainy. And that was the one single most vital information I was looking to see every day, because I found that among all the news that exists in that newspaper, That was the only thing that relates to me, because it would decide after I come home from school whether I get to play or not. Because if there is rain, we cannot go out to play. So at an early age, unconsciously or in my subconscious, there was always this problem. How do we know about this well ahead of time? I cannot. I don't want to get my free time ruined by rains. So it started stemming in before I realized. And then, of course, with my dad taking our family to trips, we used to go very frequently to the Northeast, to the Himalayas. And we have traveled widely, and he used to point us to all the different kinds of landforms, the different flora, the fauna. And it kind of became of natural interest for us to question, oh, why do we see this kind of trees here? Oh, why do we see those kind of animals there? Oh, why don't we have rain here? So it became a natural part of our conversation, and it very nicely tied up with the things we were learning in geography. I used to love geography, and it became very interesting because while learning geography and physics and math, you develop those analytic logic sense, and you can easily connect all the different parts of the whys, wheres, hows, if you just think. And so it became a very easy subject for me because I didn't have to remember anything. I didn't have to memorize anything because I could understand why it rains in some place and why it doesn't. So, fast forward, we finished high school, went to college. I studied physics. I wanted to study geography, but at that time, nobody would give me a geography honors because I didn't have geography in my high school subjects. So went and studied physics, then went to the university, science college, did again another master's in physics. And as we are going through all of these learning, experiences, competitions, getting chances, all those are, of course, very difficult job. And we were very lucky to sail through, our efforts, our academics there. But one thing was very, very strange. Like when we study physics, particularly a subject like physics, we have a lot of assumptions. We have to assume 100 things before you get to an equation and start making actual progress. But as soon as you think and stop and try to apply that physics to a real world engineering problem, you would see that most of those assumptions don't work. Life is not linear, not Gaussian, not normal, not steady, not uniform, and it changes with time. And so does a lot of things, a lot of engineering problems. So many of those assumptions do not work. And I started getting worried that, oh, with all this knowledge, what do we do? Because we cannot apply it anywhere, if we have to do engineering and solve real world problems. So as I was doing my master's in physics, I developed a keen interest in mathematics. I mean, I was always scared of mathematics, thinking, oh, that's such a difficult subject. And there were so many of our friends who were good in maths. So I was always worried that I didn't understand it well enough. But as I started, going in through my higher education, I realized how the math was connected to the physics and how the physics was not going to work without the math. And so they became somewhat, symbiotic in relations as we studied. And we soon figured out that once you go from the realm of theoretical physics to applied, all the world changes. So that's what took me to Indian Institute of Science. I did my master's in civil engineering, also called, part of my work was in earthquake engineering. So that paved the way into applied dynamics, applied sciences. And from there, I did my PhD in looking at climate data from an engineering perspective. So I learned about the climate science, the subject climate science, in quite the reverse way, looking at the numbers, looking at the data, and trying to understand what the data tells us, instead of going through the traditional way of learning a subject. So all of that got my interest up into the earth science, climate science. I must also acknowledge my, inspiration I got from my parents, my dad, and also my friends. Particularly one of my very close friend, she was studying geology, and she would go to this amazing. Sorry about that. It's a wrong time people choose to call. Okay. Yeah. So I forgot where I was. Sorry about that. So yeah, I was trying to pick up my interest in earth science, and my friend uh, Devlina, Dr. Devlina Banerjee, uh, she was a geologist, and she used to go to different places, look at mountains, do field work there, and she would come back with so many stories, and I would learn little bit from her across dialogues on the earth science, and that also fueled my interest. So anyway, then I went to climate data science, and that's when the fun began. So, how do we understand climate change? Now, let me start sharing my screen, and let me see if you can see. Okay. I'm sorry, I have to start from the beginning. All right. So, yeah. So that's why I named my talk today that how do we talk about my journey? Could be your journey too, towards understanding climate change. So it all started from Rajabajar Science College, in University of Calcutta, the famous seat of physics and so much of learning and achievement in our country. Having done my master's, I went to Indian Institute of Science, which opened up lots of possibilities, lots of exposures to what you could do with the science and math. I'll not spend too much time on them. I'll come back later if you have questions on how to get there and stuff. Then I did my PhD from Jawaharlal Nehru Center for Advanced Scientific Research, particularly the Engineering Mechanics unit. And the interesting thing about that is it was a smaller institute at that time, a young institute, but it had collaborations with lots of international entities all over the world. And after finishing my PhD, for a few years, I worked as a catastrophic risk modeler in the insurance industry here in the Bay Area. I got married during my PhD, and that's how I came here, and then worked in the industry for a few years. And then I got a chance to work in Lawrence Livermore National Lab for my postdoc. So the interesting thing is, when I was working as a catastrophic risk modeler, I was in the business of modeling, risk modeling for hurricanes, tornadoes, severe storms, earthquakes, fire following earthquake, and so on. And I was always asking the question that one element that all of these studies are missing is that they do not know when the hurricanes are going to come and where. And, are they going to be very strong? What would be the wind speeds? So questions like that kept coming up in my mind, and we had no answers from the engineering problem that we were solving. And I was always thinking that maybe the climate modeling, understanding the climate as a dynamic system, can help us get there. And so I applied here, and I was very lucky and fortunate to qualify through their exams and got in through the interviews. It's a very prestigious place. And I worked as a postdoc in this Atmosphere, Earth, Energy Science division they had as part of the IPCC Working Group 1 in the my job was to basically understand and study what are the ways in which we can reach abrupt climate change. Um, so during my work, we were looking at, large scale simulations around the world for hundreds of years together to understand what in fact would the climate look like 100 years, 200 years, 1000 years from now, and which areas are going to become drier, which areas are going to become warmer, or wetter, all those kind of thoughts. But unfortunately, although it's important for us to know that what is going to happen so far ahead in the future, but we need to still know what is going to happen tomorrow, 2 years from now, 6 months from now, 5 years from now, because all our decisions range around that areas. We are not really thinking that, oh, what would happen 1,000 years from now? That's not our current worry, or is it? So questions like that made us go to the next step and create, together with my friend and colleague, we came up and formed this company called Climformatics, where our goal was to be able to predict localized climate and help prepare businesses, communities, industries, governments, all kinds of stakeholders to be able to protect and mitigate their risks of climate change. Okay, so now let's understand what in fact are we looking at when we are talking about climate versus weather. I'll stop here and just give you a few moments to respond back, particularly to the students, to see if you have any ideas of what is weather and what is climate.
Ma'am, weather is the condition of environment for a short period of time, and climate is the opposite.
Correct. So it's basically, if we can think, the entire Earth's climate system is having its own dynamics. And these dynamics vary across different scales, not only in time, but also in space. And so weather is what we see, what happens to us on the surface of the Earth for 1 hour to 2 weeks. Usually that is the time span of how weather changes. But climate is something long-term. So usually if you're staying in Calcutta, you are used to a warm climate, not so much cold. How do we get that notion? Because we see year after year, the same pattern is repeating. So that's the longer time scale, which is climate. But when we are thinking of the dynamics, things keep changing, in a continuous fashion. So within the first week to first 2 weeks, you have the weather phenomena. Then you start to, as you get to the month, you start to have longer time scales kicking in there. It's like you're having subseasonal variations, which is anything between 15 days to few months. And then you get to seasonal variations, then you get to annual variations. So that is how you're gradually going from a weather scale to the climate scale. However, when we are talking about models, a model, do you know what's a model? What do you understand by a model? Anyone?
Ma'am, a model is essentially a simulation of a phenomenon which can be seen in the environment.
So yeah, correct. So a model basically mimics the behavior of the actual system. And we can study the actual system, things that are changing in the actual system by studying the dynamics in the model, provided we have understood that dynamics and done the model correctly, right? So in doing a weather model, we need fewer things to understand. We need to look at the atmosphere, the wind, the sun, this amount of solar radiation, rain, clouds. Those are pretty much, and of course, we have some interactions with the evaporation, transpiration, humidity. So those are the things that are varying in a short scale, and that's weather. But when we go to longer term, then we have actual interactions that happens between the sea and the land and the glaciers and the vegetation and also emissions, right? And so once all of these different parts of the climate dynamics, they interact each other, and they also interact at different time scales. So the time scale with which the air interacts with the sea is different than the time scale that the glacier reacts with the land, or the vegetation reacts to the ocean. So everything has a different time scale. And as we go into the climate scales, we gradually go into longer and longer time scales, which spans from year to few years, decades, centuries, and more. So the climate model is capable of actually mimicking all of these interactions, right? Okay, now let's go to the next slide. How does it go? All right. So weather is a fast-changing transient phenomena, whereas climate is a slowly changing phenomena with robust steady-state dynamics. And I hope to show you...
A common mistake when interpreting statistics is to look at them from too short a distance. This can make everything unclear and confusing. So forget the details and take a step back. You're looking at a dog when you should be concentrating on the owner.
Let me start this again. You might have missed the beginning of it. This is just a quick way of understanding what the difference is.
A common mistake when interpreting statistics is to look at them from too short a distance. This can make everything unclear and confusing. So forget the details and take a step back. You're looking at a dog when you should be concentrating on the owner. As you can,
ma'am, we can't see the video.
Leaping in bounds.
Oh, okay. Then I will just not.
I think you have to start from the beginning.
Are you able to see the cartoon picture?
No.
Not.
No, ma'am.
Oh, okay. I see. Let
Ma'am,
me.
it is the weather versus climate slide which we can see.
Okay, so.
A common mistake when interpreting statistics.
Are you able to see now?
Them from too short.
Yes.
Oh,
this
okay.
can make it unclear and confusing. So forget the details and
let me start again.
Back.
Yeah, this will just get your ideas very clear on how modeling is and what
mistake
can
when
be
interpreting statistics is to look at them from too short a distance. This can make everything unclear and confusing. So forget the details and take a step back. You're looking at a dog when you should be concentrating on the owner. As you can see, the dog is all over the place, leaping and bouncing, sometimes upwards, sometimes downwards. But where do you think it'll be in 10 seconds' time? Around here, right? But at this moment, the dog is on its way downwards. So why do you think it'll find itself up there? It's because you've noticed the owner. The owner is the trend, and it's he who determines where they both will be in a while. It's a bit longer than a couple of dog bounds. He could change direction. There's a lot we don't know about this guy, but everything we do know indicates he's heading in that direction. The owner is the long-term trend. The dog is the variation around this trend. Or the owner is the climate, the dog is the weather.
So wasn't that cool?
Yes, ma'am.
Right.
Yes, ma'am.
Yes, I just thought it would be,
That was beautiful.
Thank you. Sometimes small things like that help us understand. So I will show you some more, little bit more now on what climate modeling is. And bear with me.
Here are shown results from 1 degree ocean by 2 degree atmosphere grid configuration of the model. Typical resolution.
So let me stop it there. So I just want to give you an idea that how do we model, right? Now we have to understand what the Earth's climate is going to be like. But for that, we need to first understand in little tiny bits and pieces, if we draw those grids around the Earth and try to understand what is the change or what is the dynamics happening in each small grid, then we not extend that, but then we try to do summations like, for those of you, you're familiar with integral and differential calculus. So when it's an application of both differential and integral calculus. So we break it down into smaller elements, analyze the dynamics there, and then bring integral solutions to integrate the whole around the whole world. Basically, that's the idea. I mean, it's of course much complex than that, but this could be a simple cartoon of how to go ahead and do that.
For current generation climate models. At this resolution, smaller than grid size features like storm systems or ocean eddies cannot be explicitly resolved, and their effect on the energy balance is parameterized.
So yeah, I'll stop this so that I can explain. So we can play around with different sizes of the grids. So when we make bigger grids, we see the large scale effects. When we make the grid smaller and finer, we gradually start seeing the smaller scales like clouds. They need very high resolution. So this is explaining that.
In the model. Although at this resolution, we cannot resolve features like storm systems or ocean eddies, we can do so in higher resolution simulations.
Right. So it's just giving you a little glimpse of how modeling is done. And how do we see this?
Daily fields for year 2000.
So when we see the results, like this as to how it is going to change.
Precipitation is shown with black contours, usually present over the red color maximum fraction cloud fields.
Okay, and we can see similar things in the temperature. Let's see if I have a temperature.
Daily fields for year 2000 of sea surface temperature. The black arrows indicate wind streamlines, which demonstrate large-scale atmospheric
temperature,
circulation.
wind, rain,
These
clouds.
are closely related and follow the large-scale atmospheric.
Yeah, so I just want to, give you an idea. Let's see what happened now. Okay. So a natural question is, what is the use of understanding it and what do we do about it? Now, there are several ways we are always hearing, several things we are always aware of and hearing, any media, news reports and journal papers that you study, that we are talking about emissions, the greenhouse emissions, as a big driver of climate change. Now, climate can change due to many reasons. It has very variable system. It's a chaotic system. It can change due to multiple reasons, but all those reasons are natural except for the human created emissions, the anthropogenic impact. Now, because of those human created impact, we are seeing a lot more changes in the climate than the climate I grew up with not so many years ago. So now we are sounding this alarm that we must do something about it. One of the main things that we need to do is to curb our emissions, curb fossil fuel emissions. get rid of plastics, do recycling. But with all of that, we are still not getting at a point where we need to be so that we don't get into extreme events in terms of climate change, in terms of higher category storms, hurricanes, like we are seeing even in the eastern coast of India. You are having larger and larger super cyclone kind of storms coming in more frequently now than it used to be before. And that's the same story here in the US. On the eastern side, we have repeatedly the hurricanes coming over Florida, on Texas, on the eastern side. And then we have these big atmospheric river systems that are delivering huge amount of rainfall occasionally here in the West Coast, Oregon, Washington, California coast. But still not enough, because California has been in drought for a long time. So conditions like that. And recently, if you're watching the news, over these 2 weeks, there are blizzard conditions in many places in Europe, which are not normal, because many of those same places were having wildfires just over last summer and fall. So definitely we are in these changing conditions, and we are getting into more and more intense extreme weather related events all over the world. And so what do we do about it? Certainly we have to curb emissions, but is that enough? So there are a lot of efforts across the climate community to work on climate restoration techniques, like technologies. People are coming up with innovative technologies. For example, we are just starting a collaboration for saving the Himalayas. The glaciers there are melting, and this large amount of water, the fresh water, which is so needed the world over, is causing floods because the rivers are overflowing. And if they're not causing floods, the huge amount of excess water are going directly to the sea, and you're having possible submerging of the Sundarban areas. You're having sea level rise there, and the coastal cities are all getting affected. So what are some of the things that we can do? So my next part of the talk would be taking you through some of the things we can do, and a particular technology that we have been testing and writing about and telling the world about. So this is our work together with myself, my colleague, Dr. Detlina Ivanova, also from Climaformatics, and Dr. Leslie Field, who is the founder of Arctic Ice Project. So what Dr. Leslie Field did is she came up with a set of materials and designed hollow micro glass spheres, like sand, like hollow glass sand, and with high reflectivity. So we're trying to see that if we do spread this on the Arctic sea ice, is it possible to reflect the sunlight and therefore keep the sea ice cool and not let it melt away or slow down its melt? And if we do so, what in fact would be the impact of that, not only in the Arctic, but around the world? So climate modeling gives a large amount of gets a large amount of use from understanding the impact of those solutions. So for example, why should we model and simulate climate restoration solutions? Well, field experiments at scale may be risky, harmful, irreversible, and expensive. And we have to remember there is only one Earth. We cannot play with it, right? So to evaluate the basic risks and benefits of the technology before they're field tested and deployed, we need climate modeling. We need to assess the impact of implementing such technology globally, regionally, zonally, locally, over the near term, long term, effects on the marine life, ecology, terrestrial habitats, effect further on the socioeconomic aspects, impacts on human health, food security. And so it serves a huge purpose in risk assessment. So we have to design these climate modeling technologies to address specific questions like, when is a good optimal time to deploy a solution? Where should it be deployed? Regionally, globally, how often? What in fact would be the impact of withdrawing such a solution? Are the changes reversible? Will they change the basic climate variability? So, and then all of this adds up to the basic trade-off between what are the positive effects and adverse effects. So I'll just present here briefly this study, and then we move on. But please stop me, to ask questions. I'll be happy to answer. So this project, particularly, these are some of the pictures of these small hollow microglass spheres with high reflectivity. So if you just look at bright eyes, they reflect 90% of the sunlight back and let only 10% go through them and get absorbed. Bare eyes does only 50%, and 50% gets absorbed. But the ocean mostly absorbs all the heat and reflects only very little. So these non-toxic hollow glass microspheres that Arctic Ice Project came up with were field tested in Minnesota, and they are very cold areas, northernmost parts of the United States, and they do the field testing, and then we get this cycle that we test, then we see what the results of those tests are, we implement them in our model, and then we monitor. So that completes the full cycle. And we have a publication, if you're interested in, where increasing Arctic sea ice albedo using localized reversible geoengineering. I would not go into this, but I would just say that the results were amazing because we could increase summer sea ice with that method. And imagine, we haven't actually deployed, but because we are capable of doing climate modeling, we are able to see exactly what impacts could be if we go ahead and do this in the Arctic. And so now we are starting looking at, okay, we would have a modestly lower Arctic average temperature. We would have, increase in summer sea ice. And then how that's going to affect things over the tropics and mid-latitudes. These are a lot of details. So, if you're interested later, we'll come back. I just wanted to give you an overview of what is possible. Not only you can see temperatures and precipitation, but you can also see which areas in the world will get droughts or which areas in the world will get wildfires. And so if you look at this graph, it's basically 3 different experiments that we did, which shows how the fire weather in October 2080 is going to look like. So again, California is usually placed with a lot of droughts and wildfires. And we are able to see that if we do a tiny bit of, increase in sea ice albedo with this material in the Fram Strait, In that case, Fram Strait is a strait between the Greenland and the North America. And that is the channel. I wish I had a figure for that here. I'm sorry. That is the channel through which all the Arctic ice flows into the Atlantic. And because of the changes in the global climate, the temperature that change, when you have a global temperature of, say, 1 degree change across the world as an average, usually for the Arctic, it changes by 6 to 10 degrees centigrade. So the effect is certainly non-linear. So we saw that in that small strait, if we do deploy these materials, they do slow down the flow of those ice into the Atlantic, and the flow starts pushing the ice back towards the Arctic core. And so with that, we see that, if we leave it at business as usual, we'll have fires here in California, this California southern part. But if we do the intervention, either wide scale into the intervention or tiny scale over the Fram Strait, suddenly things become cool. And so the fire weather index reduces, which is hopefully good for us. Another topic I wanted to bring up, I don't know if you're aware of this. Below the Arctic, there is a lot of these substances that are available, which are called methane cladrates, or popularly they're called as fire ice. And these fire ice are like gas molecules, which you see here, but they're trapped inside ice cubes, and they have structures of ice around them, but inside that they have the gas, which is usually methane. Now, these gas deposits are found where? They are found across, below all the, many of the seas of the world. They're not a problem as long as they are kept cool. So, they're lying in very low temperatures and under a lot of pressure, which is the condition usually when you look to, the seas of the world. They are very deep. And so the chances of the methane outgassing from those depths of the sea are rare. But the problem is, in Arctic, there's a lot of shallow areas. Arctic is in general a very shallow sea. So the cladrates which are lying below the Arctic can easily outgas if there is a change in the temperature of the Arctic ocean bottom, temperature at the bottom of the ocean. If that changes, then it easily liberates this methane gas from those depths, and they come up as bubbles to the surface, and they they're just imparted to the atmosphere. And if they mix in the water, then they create ocean hypoxia because of the chemical reactions. Both are bad, but if the methane goes up to the atmosphere, that is very bad, because that produces instant warming of the temperature. And then if you have warming in a cool place, then it feeds back into the dynamic system and produces, more ice loss and more melting and more warming. So it is important we keep the Arctic cool so that these cladrates don't outgas and create runaway warming. Part of my work at Lawrence Livermore was to study the impact of methane coming out from this cladrates, emanating from cladrates, particularly in vulnerable locations in Arctic. And this is actually a plot from one of my work papers. which shows in this circle all the things, all the areas in red and red boundaries are hotspots for the availability of the methane clathrates. And this you can see, okay, here I can show you the location of the Fram Strait. So Fram Strait is right here between Greenland and Svalbard. And this is the Arctic, if you look from the satellite image, satellite projections. This side is the East Siberian side. This side is the North American side. This is the Canadian archipelago. And this is Europe, Norway and the north of Europe. So what happens is in these red regions, there are lots of clathrate deposits. And then you have these big rivers, Who can name some of the top largest rivers in Russia and Europe that goes and empties themselves to the Arctic? Anyone? Okay, never mind. So there are rivers like Yenisei, Lena, what is the other one? Ob, yeah. So all of those, sorry?
Yeah, Ob.
Yeah. I'm trying to remember my childhood geography. So yeah, those big rivers, they carry water and a large amount of water, fresh water that goes to the Arctic. And the places where they meet the Arctic, often you have, geothermal activity going underneath, and that actually is warm, produces warmer temperatures and produces conditions where these Arctic clathrates below the surface of the ocean, on the ocean sediments in the shallow parts of the Arctic can melt. So the work that we are doing right now here is in this location between Svalbard and Greenland, this narrow Fram Strait, we had studied by doing models as to if we can deploy our hollow microglass spheres, which are highly reflective in the sea ice here, then it kind of slows down the flow of sea ice melt and also the flow from the core of the Arctic to the Atlantic. But we are still testing the solutions. And okay, so now we are going to talk about what we can do in climaformatics to help predict, prepare, protect, and how all of this modeling, data science, predicting, all can come together in helping us solve or address or mitigate or become resilient to the problem of climate change. So climaformatics was born with a mission that we can predict future climate to proactively mitigate risk and drive better business decisions. So the climate change is affecting our world in various ways, either in form of extreme and severe weather events. It impacts our lives, our livelihoods, businesses, food security, shelter, communications. It also impacts each of our lives in more ways than we can say. We can lose our homes, we can lose our productive land on which we depend to grow our food. It can just cause us a lot of healthcare issues. For that, we need to, our cost of healthcare rises. It creates and drives insecurity, drives an uncertain future. So what is the problem that we specifically are trying to solve? You could say that, well, there are a lot of these big IPCC models. Why can't we use them to solve the problem of climate change or to better understand what our rainfall, temperature, wind, and so on is going to look like? And with that, when we try applying the models as they are, The problem is they don't have very high spatial resolution. They cannot resolve between less than 100 kilometers. So this is an example that shows that for both these two locations, which are just about 8 miles apart, and this is a location of Santa Barbara in Southern California. And you can see the gray bars are all rainfall that's forecasted by these big climate models from NOAA. How many of you have heard the names of NOAA? So NOAA stands for National Oceanic and Atmospheric Agency. It's like the atmospheric, let's say, like a headquarter of all things that are happening with climate science. NOAA and NCAR, National Center for Atmospheric Research. Also, some of the work gets done in NASA, the National Aeronautics and Space Agency. But all of these models, and also models from elsewhere in the world, like all the countries, many of the countries have climate models of their own in Europe, in Japan, in China. So all of them put together come up with these kind of forecasts, whereas the observations are what you see in blue. And this is not one, but you can see at least 4 or 5 years of data here. And so the average accuracy of these models are not good. For example, in this example, they are off by 170 inches per season. Whereas if we can do some little bit of math, which is what we do, we can get a better estimate. The greens are our predictions, and you can see they're far closer to the actual than what the big climate models predict. So the solution is actually, we need to have longer term weather and climate forecasting, which are more accurate. And what we are trying to do in our work is basically bridge the deficiencies that exist in the climate model technology using data science. Now, I don't want to go into all of these detail. I'll show you that with those technologies, we can predict the fire weather and how predicting the fire weather and extreme events can actually shift how we look at risk. So for example, if we can do climate prediction well, then from that, we can do modeling for various things like wildfire risk, storm risk, extreme heat, drought modeling, flood modeling. And together, if we also try to start doing, small things that can cool down the planet, that can change or make the planet more climate stable, like, work has started in the Himalayas in restoring some of the lost deforestation areas. They're trying to plant more trees. We are trying to bring a change by organizing organized to eliminate the black carbon soot that is caused by some of these, indigenous stoves that people in the mountains are burning for either heat, warmth, food, cooking. So if those could be changed by smokeless and sootless stoves, that could stop it. That could make a small change. So each and every of these small changes, if we can be conscious and not pollute as much, all of that are small steps that we are going to take that will help us restore the climate to normal conditions which we had before. And so modeling and prediction, if we can bring them together, then we can achieve a great number of things. So we propose these integrated solutions to climate change, where localized climate prediction with climate restoration and catastrophic risk modeling together with localized climate prediction can be one complete circle where we can basically use this as a predictive way to understand and restore and make our planet more livable and adapt to the changes that we are faced with. So feathers in our hats, We went through several competitions. We won some of them because of our ideas. We were fresh from the lab. We are not business people. We are scientists, but we tried to go ahead and compete in the business community, saying that there's a business case in doing and helping with the climate. And with that, we won some awards and accolades. Our massive transformation purpose is to be able to help humanity prepare for the inescapable impact of climate change. Thank you. Any questions?
Please let us start the interactive session now.
Yes, thank you so much, ma'am. I think the students are very eager to interact with you, and I'm sure they have questions. So I can see some raised hands. Who are these? All right, let me take some questions. I think Ananya, have you got? All right. Arag, you've got a question, please ask.
Yes, ma'am. Thank you, ma'am, for giving us this knowledge. We are so inspired and thankful. And my question is that you talked about non-toxic hollow glass microspheres to spread them, and it will help us to prevent the ice from melting. So is there any side effects that will cause, you talked about the positive side. So if you could enlighten about the negative sides as well.
So far, it has been tested and it's still undergoing toxicity tests in labs. It has passed through several sets of examinations and has been declared safe to go and do field testing, but still more testing is underway. And we are in the process of studying the global impacts as well as the regional impacts to see what in fact would be the effect, if at all, any adverse effects. So climatologically, we didn't see anything adverse, but more needs to be done, more needs to be investigated. So as a follow-up of that, we have started working on a larger area on the Buford-Gyre. Do you know where Buford-Gyre is? Let me show you quickly. Hang on. I just stopped sharing my screen. Let me do that once more. So in the Buford-Gyre, we are actually doing this work at a large scale to understand. Let me take you. This is a discussion for Himalayas. I didn't have time for this, but I can show you the before. So, this could be also one example. So if the graph that you see on your left here is actually, if we don't do anything, 2041, this is at the end of, summer when the fall starts, September. At the end of that, we are going to have very little amount of sea ice. Whereas if we put this material, then it can increase the sea ice area. And similarly, we are now testing through, let me show you the Buford-Gyre work. So now we are testing this region, which is the Buford-Gyre. So this is still, you're seeing the top of the Arctic, top view. If you were to be on a satellite and look down, peering on the pole, this is what you see. And all these are different directions of the ice drift. And so there is a circulating motion happening here. Sometimes it goes in the clockwise direction, sometimes it goes in the anti-clockwise direction. But the exit route of these motions are through the Fram Strait, which is here. This is Greenland, this is Svalbard. This side is Europe, this side is Russia, this side is Canada and North America. This side is America and this side is Canada. So anyway, now we are trying out in a larger area to see, we haven't gone there physically yet, but we are doing the simulations so that we can see what in fact would be the effect. So it's still ongoing studies and it is not yet, we have to get permission from several nations to be able to go and test it on site. So hopefully
Yes,
that gives you some idea.
Yes, thank you,
Thank you,
ma'am.
ma'am.
Ananya Sinha, I think I can see your hand raised. If you can ask a question.
Very good morning, ma'am. Ma'am, my question to you was, what are the analysis techniques that Climaformatics uses in order to research about current climate change, and what IT skills one must have to work in this field?
If you ask me, I use very much mathematics, statistics, signal processing, which is something that you learn sometimes in electrical engineering. So let's discuss some of those techniques and technologies. So what happens is, once you start looking at a time series, so these are large scale time series. You know what a time series is? Some variable which varies with time. But in these cases, in the climate space, they're not only varying with time, they're varying with space. They're often varying with height, altitude, right? You can have temperature at different layers of the atmosphere. So you do have a lot of dimensions to a single variable. And so you need to have the capability of parsing down information to get to where you want to. And to be able to do that, you have to apply a lot of fundamental mathematics. And that fundamental mathematics is also backed by fundamental physics. So imagine the dynamic systems work like you may be reading in your coursework about simple harmonic motion, a pendulum, right? You have studied a pendulum, or you have at least seen one. So what happens? Like a pendulum keeps oscillating, right, in simple harmonic motion. And then you pull it a little bit and you leave it, it will oscillate some more and again come to its equilibrium position. So our Earth's dynamics is somewhat similar to that, except that this pendulum that we call as Earth's climate dynamics is very complex. It has too many moving parts. So imagine now, instead of having one pendulum attached to one string, you have all kinds of strings, big and small. The pendulum balls are also having different masses, different materials, different lengths. So then suddenly your simple harmonic problem becomes very complex, isn't it? You have a lot of commensurate dynamics going on there. So Earth's dynamics is somewhat in a cartoonish manner like that, when a lot of things are oscillating and changing all the time. And so you have to know how to be able to apply, how to take each one of those pendulums apart, and also how do they each talk to each other, and then how do they talk to everyone. So it's like a conversation. If you want to turn in, think in terms of conversation or music, it's like everybody is having a role in that. It's a big orchestra. So we need to have very detailed amount of signal processing, statistical data processing, multivariate kind of analysis, multivariate, multi-scale, multi-resolution analysis. You may not have heard this or be familiar with these words, but as you learn through calculus, as you learn through linear algebra, things that you start learning in your high school, you will get there.
Thank you.
I hope I didn't sound very scary.
Thank you very much, ma'am.
No,
and what you do with, okay, let me add to this, because I think a lot of weightage is right now put under words like artificial intelligence, machine learning. But I can tell you from experience that the best way to learn about all of those technology is to be grounded in your maths and grounded in your physics and grounded in your statistics, because these are the main pillars that you will need to do any kind of data analytics. Whether you're studying, biology, medical, you're studying how the heart hearts, rhythms are, or signals that's going on in your brain, or the Earth's climate system, or the earthquakes that happen. All of them require these same kind of tools. It's just the nature of the problem changes. And based on the nature of problem, you start specializing in solving one kind of problem.
Yes, thank you, ma'am. I think everybody should keep themselves on mute. Manav Sharma of Birla Divya Jyoti, I think your hand is up. If you want to ask your question, please.
Good morning, ma'am. My question is not related to this topic, ma'am, but my question is related that, ma'am, if in one place there is a drought and in the other place the water is overflowing, ma'am, there can be any other affordable way to transport the water from this place to this place?
Very good question, Manav. And people are trying to do some of that thing everywhere in the world, or in many places in the world. But it's not easy. To move water is very expensive, and droughts in themselves are very debilitating. But there are engineering technologies like taking water using aquifers. Aquifers are like big pipes that carry water over long distances. Actually, you'd be surprised to know a lot of the water that comes in Southern California. So Southern California is a very arid area, drought-stricken area that doesn't have big rivers. The nearest river that is big and gets water is Colorado, which is miles off. And so people have the lakes in the Sierra Nevada mountains, and that's where fresh water collects as the spring happens and the snow melts. And that water is collected and taken through pipes called aquifers and canals, and supplies to big cities like Los Angeles. So it does happen.
Thank you, ma'am. I just wanted to add perhaps one line as a geographer that I think the effect on the ecosystem of transferring water from a flooded area to an area of drought has to be considered, because a long time back in Jodhpur, there were floods because of the Indira Gandhi Canal in India. So I think the ecosystem needs to be taken into consideration. Just wanted to add that.
Absolutely, absolutely. This is not like you can dig a canal anywhere and everywhere. That is not going to happen. You have to take care of the ecosystem. You have to take care of the, all the water cycle considerations. And also there are a lot of socioeconomic impacts. So here I know of technologies where people are trying to solve the problem of, carrying water or distributing water, also along with, saving the water from getting evaporated by putting solar panels on top so that the canals get covered and they also generate electricity, and that electricity helps to carry the water from one place to another. So there are a lot of, surrounding technologies that are happening currently.
Yes, I thank you, ma'am. Yes, a similar thing in Gujarat, I think. Yes. Priyanka Bardia, your question, please.
Yes, ma'am. Thank you, ma'am. Good morning, ma'am. Thank you for giving us this. Thank you for making all these complicated things so easy to understand.
They're easy. No worries. They're not complicated.
Thank you, ma'am. Ma'am, my question is that you said for us to be able to curb climate change, one of the things we can do is reduce the use of fossil fuels. And we are slowly starting to use, renewable resources like solar energy and wind energy. But ma'am, do you think it is possible to fully eliminate the use of fossil fuels?
Well, I do not know what is the best way to answer that. On one side, we are humans. We are we get used to our habits, and habits are hard to change. But there is a serious effort across the world to reduce fossil fuels or to channelize the necessities using renewables. But even there are still challenges that have to be solved in the renewable sector in terms of some of the technologies could be cost prohibitive. Some of the technologies could be still generating or contributing to pollution in different ways. So we still have quite a bit of research and engineering to go. But definitely, if we can all take small steps in our own lives, consciously making decisions of not wasting power, not wasting water, not throwing junk and plastics into landfills, trying to recycle, reuse, to have a measure of conservation no matter what we do. And that goes a long way. And that also, drives into our values, our ethics, our compassion, empathy, everything. It really defines who you are.
Thank you, ma'am. I think the next person is Riddhi Datta. You have got your hand up.
Good morning, ma'am. My question to you is, how will your current research that is developing the fire weather prediction capability help the mankind?
Oh, that's such a nice question. Thank you. So our goal is, I don't know if you follow some news from California here. We are having an increasing number of wildfires. And as humans, we are gradually, going and encroaching into the wild areas like the mountainous regions, interacting with the wild animals, interacting into their space and going and building our homes there, roads there. And because we are going and settling in these mountains, now we need all the earthly pleasures. We are not cavemen. So therefore, we need electricity, we need water, we need convenience stores nearby, we need good roads to drive to our houses up in the mountains. So all of that has created a need for electricity source of power and energy and all of that in those remote areas. And what happens typically is that you do have these strong winds. What are the conditions? Let's see, that generates to this wildfire conditions. You have to have strong winds. You have to have a very dry climate. You have to have fuel that is ready to burn, live fuel or dead fuel. And if you have houses, which are here, most of the houses are made of wood. And so all of that is like you're putting a lot of fuel, getting ready. So if there is a spark from an electrical facility, a grid failure or a transformer failure or something fails, and it can catch fire, and that fire somehow keeps spreading through the mountains in an uncontrollable manner. And so if we can understand that such a condition of fire weather is coming well ahead of time, if we can give, say, 1 month ahead notice that, hey, in 1 month's time at this particular location, you're going to get very high fire weather, fire danger conditions, then you can take measures. You can cut all the, say, if you're staying there, you can cut all the bushes, shrubs, and grasses and things around your houses. You can find water to keep them a little bit wet so that they don't catch fire. If you're an electricity supplier, you can shut off your power at those times for some time so that the high wind doesn't make your infrastructure fail, installations fail. So all of that planning can help save lives, can help save huge amount of losses. And people become homeless in those situations overnight. And it takes years for them to get their life back. So it can really be helpful. We may not be able to stop the naturally occurring wildfires, but we can give people enough warning to move them out of harm's way, to secure their properties, to secure their businesses, to not end up in a total loss. So that is how we can help. Does that answer your question?
Yes, I suppose so. Yes, the next
Yes, ma'am,
person.
thank you.
Yes, Alaina Kamar, I think, is waiting for some time. Alaina, yes.
Yes, ma'am. So, ma'am, looking into the Climate Change Performance Index in international climate politics, which enables comparison of mitigation efforts. So, which country tops in the Climate Change Performance Index and what strategies they may have implemented?
I am not up to date on those statistics at all. I'm too busy doing and working with the solutions that we have and associated
So
issues.
I think, yeah, I suppose it's Denmark. Yes, India comes 10th over there. I was just looking it up a bit a few days back. So just because we were going to do this session, so it's Denmark, and yeah, all right, we'll go to the next question. But what strategies? It's very difficult, I think, to predict that. Like strategies differ from country to country, I suppose, ma'am, don't they?
Oh yeah. Those are very different topics.
Yes.
And so just as you know, just so you know, we are recently have been invited, and we are now members of the United Nations Disaster Risk Resiliency Forum chapter for the US. And there has been a lot of collaboration. There is a lot of collaboration across countries here that work together, exchange knowledge, exchange engineering resources and solutions to come up with better solutions for sea level rise or flood risks and things like that. So I think with all of that, those collaborations, we would converge to a positive place.
All right. Anybody from Shiliguri school? Nobody is there from Shiliguri, the guest school. Then I would ask them if they have got any questions. Shiliguri, nobody. All right. Then we can go on to I think Aditri Agarwal. Aditri Agarwal, your question, please.
Good morning, ma'am. So it is so inspiring that in spite of being such a busy person, you can manage to take part in Indian classical music concerts. So could you please enlighten us with some tips so that we can also find a balance between our academics and our hobbies?
I love that question. The truth is, if you are into any of this performing arts, like music, for example, even if you don't find time, and you think, oh, you don't have time for all of these, I'm leaving music and I'll not practice. That may be up to you, but music is not going to leave you. So you will keep coming back. And so I think for me, I trained in Indian classical from a very early age, all throughout my school career, school life. And then in between, when I went to Indian Institute of Science to study, I almost stopped it for quite a few years, and I was not in practice. But again, I started little bit by little bit, myself. And when I came here, I had the opportunity of starting back again. And I started back at those times when I was most busy and I just didn't have time. But that helped me, get through my stress, get through my that was the only thing I would look for in an otherwise extremely busy schedule. So keep doing it and don't lose it, because it makes a lot of sense. And for those of you who are into Indian classical music, you'll find a lot of things, commonality between music, dance, and maths. So it's no surprise that I do both of them.
Thank you.
Thank you, ma'am.
Actually, it always gets noticed. I'll tell you, I'll share this story from my experience in Indian Institute of Science. So when I went there, it's an extremely cutthroat, competitive life there. Like every day you have to be on top of your homeworks and assignments and tests, and the whole class is the best of the best in who have come in. And it's hard. Like, it's not that you can sleep in peace saying, oh, okay, if I don't do this homework, nothing much will happen. It will happen. And so in order to keep yourself sharp, you have to be all the time at the top of it. And the courses are hard, and they're international level. And I mean, you can go into their website and see. But what I'm trying to say is, even there, sometimes we will have conferences, we will have opportunities to actually go and perform something. And somehow, because of my background and having come from Mahadevi Birla Girls High School, there were few numbers which I was always ready with. And can you guess which numbers were those? They were those prayer songs that we sang all through our life. And those prayer songs actually kept me going. I learned later that they were, and whenever I'll go to these big conferences and not to present there, not to study or sit and listen, but I'll be called on stage at the very last moment to come and sing an invocation. And at that time, you don't have time to prepare for anything. You have been just told outside of a class that, hey, you have to go into that conference and sing a song, and there'll be big dignitaries. So I would draw back into my MV Girls experience and learning and sing those songs, and the crowd would be, oh, wait a minute, you know so much of Gita? Where did that happen? And specifically, I'll share the story. It's very close to my heart. So we had a conference where none other than later Dr. Abdul Kalam Azad, who was not then the president, but was the chief of DRDO, the Defense Research and Development Organization. He was, the main guest of honor in our conference of knowledge management organized by the management students. And I was called upon to sing there. It so happened that my parents were also present at visiting me and my brother, who both used to be in Indian Institute of Science at that point of time. And they were all part of it was management department. My brother was part of the organizing. And so I was very quickly called upon to do this invocation. And I remember I sang a lot of the Gita slokas, which I learned in school. I sang also the Saraswati Vandana and maybe Vande Mataram. And after that, I had the opportunity of this, extremely enlightened Dr. Abdul Kalam Azad come and tell me, where in which city, in which school have you studied that you learned, where did you learn this? And I talked about our school and how we did this in our prayers every day. And he said he was very impressed by it. And he said, you are going to make your, parents and teachers very proud because you remember these difficult things from your childhood. And since then, it has always been an inspiration for me. So, yeah. So don't leave your music, and music will not leave you if you love it.
Thank you, ma'am. All right, we come to the next person, I think, whose hand is up for quite some time. I think it's Gargi Datta. Yes, what's your question?
Good morning, ma'am. Thank you for this enriching session. And recently we had a volcanic eruption, which was a massive volcanic eruption at Tonga. So will this eruption affect global climate in the future?
Well, we already know many people around the world are already affected by it with the tsunami. Actually, the collaborations that we have, we are just starting off for working on the Himalayan glaciers. One of our collaborators couldn't attend the last meeting because of being affected in one of those Pacific islands. So, yeah, so they do have effect in terms of the sea level rise, in terms of, flooding risks, coastal flooding risk. Even we also lived through that warning. Here in the Bay Area, there were few people off the coast of San Mateo who had to be rescued from the waters because the tsunami caught them by surprise. And there was similar such event. There were about 3 to 4 feet high of water that happened here as well.
Thank
All
you.
right. One more. I think we can take one more question because we've got a request from Principal Ma'am, which I'll come to. We can ask Vidula Verma, please, if you can ask your question quickly.
Oh, yes, thank you, ma'am. Good morning, ma'am. Thank you for this such an enriching session today. So for my question for you is that as we know in today's world, urbanization is so important. So how can we have urbanization with no side effect or less side effect on climate change at the same time?
Very nice question. So, you can urbanize, but leave enough space to breathe, leave enough greens. And also, there are methods, engineering tools that you can use that the cities can use for planning better urban development that will keep the temperature cool, use those kind of, resilient materials that can go with the climate solutions. There are many kinds of building materials, road building materials. You can put, reflective paints. You can landscape the city with enough greeneries so that both humans and plants and vegetations can be in harmony.
Thank you so much, ma'am.
All right. Thank you. I just wanted to add, I think the children already know about the stable urban fringe that these Calcutta wetlands provide in Kolkata. Ma'am, you must be knowing about it. We've done a little bit of work with the children there. They visited. All right. The request from ma'am is if you can sing some couplet from the prayer songs we were talking about. It's from our principal, ma'am.
Oh, thank you so much. I'm happy to do, but just that I had been talking for last 3 days continuously. So I don't know how I will sound, but the risk is always with you listeners, not me. Okay. So I don't know. Do you still do those prayers in the school these days?
Yes, of course, ma'am. The children do.
And I don't know if they have changed from my times, but I can try one Gita or one Saraswati Vandana. Which would you prefer?
Children, anything?
I don't know. So I'm just trying to see
whatever you want to do. Whatever you want to do, ma'am. It's
whatever you're comfortable with.
Okay. Ya kundendu tushar har dhavala ya shubhra vastravrita ya veena varadanda mandita kara ya shweta padmasana ya brahma chuta shankara pravritive devai sada vandita samapatu saraswati bhagavati nishesha jadyapaha. Thank you.
That was excellent, ma'am. Thank you so much. Now I would like to invite our student Pragya Biswas to give the vote of thanks. Over to you, Pragya.
Good morning, everyone. Good morning, ma'am. On behalf of my school, Mahadevi Birla World Academy, I take this opportunity to convey my heartfelt gratitude to our esteemed guest, Dr. SUBARNA Bhattacharya, for gracing the back to school session with her presence. Ma'am, your versatility and dedication to work is truly inspiring. You guided us really well, taking us through your experiences and answering all our questions with patience and care. This interaction will surely help us in making our career choices. Thank you so much for this engaging session. Our
You're
sincere
welcome.
thanks. Yes. Our sincere thanks to our mentor and chairperson, Ma'am Mohata, for her constant support and guidance. A special mention to our principal and vice principal, ma'am, for taking this wonderful initiative for the students and being our source of inspiration always. With deep sense of appreciation, I thank our coordinators and teachers for their untiring efforts. I thank all the students for participating enthusiastically in today's program. Last but not the least, I specifically thank the technical team for ensuring smooth functioning of this online event. I once again thank everyone for being with us today and making this session successful. Thank you.
Thank you.
All right. I think ma'am has conveyed her deepest heartfelt gratitude, and she has written, I'm so overwhelmed today. Thank you so much for connecting and always stay connected. This is a bond straight from the heart. That's from our principal, ma'am Shaha. She's written it and conveyed it to you, ma'am. Thank you so much.
I am really overwhelmed to be here, and it's been wonderful talking to all of you. And I know some of my friends from my batch might have joined our conversation. Thanks to all of you. Really appreciate this opportunity.
Yes, ma'am, we're really fortunate to have you amongst us today. And I'm sure that your enlightening talk must have inspired some of our students to take up climatology or climate change as the future scope of studies. Thank you, ma'am.
That's great. Yeah, please feel free to reach out if you have further questions and any other guidance that you would like.
Yes, I'll be sharing the email to the students, and if they wish to, Principal ma'am will be also connecting with you, she said just now.
Sure, no problem.
So I think we can ask the students to perhaps leave, or look, if ma'am, do you want to continue? We can end the session then with your permission, ma'am.
I am more flexible. For me, it is, late in the night, so I don't have any other engagement. If you want to chat, I'm fine.
I think, but I think
want to ask you one thing. Can I? Yeah. You talked about this Arctic spraying up at that hollow scope which you are making out there to protect from the sun rays. That's how will you implement that?
That's the $1 million question. How will we implement that? So there's a separate research that's going on. Yeah, we are exploring spraying over the Arctic sea ice to go with the ship and go as near as possible to those sea ice, and then use wind blowing machines, because otherwise, dropping by the aeroplanes or helicopters, they don't seem to be economically possible. And so, yeah, we are still working out on the details.
I wish you all the best, because that's very needed. That's very much needed.
We are actually also trying to do that over the Himalayas, first over the modeling, particularly in the Gangotri area. That's where rapid loss of ice is happening.